Second to the last class. It's just tonight's lecture, next week's lecture. Those are the last 2 lectures of the semester. And then we'll have our final exam on Wednesday. So the research papers are due next week, and I wanted to answer a couple of questions I've got individually for the whole group so that everyone can understand what the expectations are. First of all, I got a question about what's the preferred format for citations, you know, MLA, Chicago style, APA, and I don't really have a preference on that. You can use any citation system that you want. So as long as it's clear to me whether you're using you know, numbers or in-text citation, as long as it's clear when you're referring to a paper that you've read, you know, if I can look at the end of the bibliography and find the information that you're referring to, then that's fine as long as you're consistent. The research paper isn't supposed to only be a summary of 6 research articles that you read. It's supposed to be synthesis. And synthesis means that you're taking lots of different information sources and you're putting it together in a coherent narrative. Like you are analyzing what you read and you're trying to find what are the similarities, what are the themes, what are differences. Basically, you're trying to put together your own narrative about what you've learned. And so, for example, if I was doing a research paper on ultraviolet disinfection, so I maybe read 6 different sources. The wrong thing would be to say paragraph 1, source 1, and just summarize the paper. Paragraph 2, my next source that I read, and then summarize that paper. That's the wrong approach. The correct approach would be to read 6 different articles, and maybe 3 of the articles talked about a new type of lamp that uses less electricity, and maybe 3 of the articles talked about different ways to estimate the dose. And so maybe if I notice that, then I would divide my research paper up into 2 sections. One about the new applications related to trying to calculate the dose in UV, and another one about energy efficiency. And in addition to the research sources, of course, you're welcome to use textbook, website. You can use other sources to gather background information to try and help you fit the research that you've learned into the context of the subject as a whole. So those are just the things that I wanted to tell you about the research papers. Are there any questions that have been lurking in your mind, or, you know, now that there's only a week left, probably you're starting to get more into the specifics. I guess one other thing I'll show you is Academic Search Premier. And probably most of you have already used Academic Search Premier in the past, but since Marshall subscribes to it and it's a pretty good resource, let me just refresh your memory about how to get to Academic Search Premier. This is a way that you can find peer-reviewed articles. So go to all article databases, and it's right at the top of the list. Academic Search Premier through EBSCOhost. So if you click on that, and then you can just type your subject. And so ultraviolet and disinfection. And then I would want it to be peer-reviewed journals, because that's the highest quality research that's done. When I do the search, it'll instantly come up with a lot of different possibilities, and you can narrow it down by things that have been published more recently. And then I can just start looking through, like, what are some of the common topics. And so if you've been having trouble finding good research articles, this EBSCOhost Academic Search Premier is probably the best place to go. And the starting place for that is just Marshall Library. All right? And one other thing I'll point out is if you go to Google Scholar, it has a nice way of formatting references for you. So look at this, ultra radiation disinfection. So if I was going to cite this paper, you just click here in Cite, and then already prepares the format of the citation. So here's how to cite that paper with MLA, APA, Chicago. So if you already have a paper that you already have found someplace else and you want to just type in the keywords, you could probably find it very easily. Like, let's see, I know a paper that I wrote, Isaac Waite ultraviolet disinfection. Let's see if it finds it. Yeah, here's one. Okay, so if I already knew of that paper and I just wanted to cite it, then you can choose any one of those. Control C, and then you go to your research paper, and then you can just paste it directly into the document at the end for the bibliography. And it'll save you the time of, it's just a little bit simpler way to prepare your bibliography. So then you just go like this. Control V, and it pasted it. All right, it's a nice tool. Questions about the research paper due next week? Why do you suppose I've asked you to write a research paper? Is it because I just like to have you in pain? Is that the reason? Why? Why do you think? It's mostly because I like you to be in pain. But the other reason, no, the main reason is because graduate school is more about learning how to teach yourself than learning a certain subject. People who have graduate degrees are assigned to unfamiliar tasks. If you graduate with only a bachelor's degree, probably your design will be designing something that's already been prepared somewhere else. But once you have a master's degree or a doctorate degree, they'll start to assign those engineers to a problem that nobody has ever seen before. And so someone with a graduate degree has to have the practice of an unfamiliar problem and learning where do you start finding about the current research that's being done in the field, because maybe your problem is on the cutting edge of some new field. And a master's educated engineer has to be able to draw together lots of different sources. Even if 95% of a research paper is irrelevant to you, maybe they'll mention one or two things. Just a tiny little bit of it will be important. And so you have to get in the habit of finding the important information in a paper that, for the most part, means nothing to you. And I've had to do that recently. I went to a conference last summer, and most of the things being talked about at that conference I wasn't interested in. They're not related to my research. But just out of the corner of my eye, I was looking through a poster session, and I noticed someone was using a new kind of stream gauge. And just hearing about that new kind of stream gauge has totally changed the research that I've been doing in the last year in a really nice way. So you have to be in the habit of consuming unfamiliar information. You know, a textbook is nice because the textbook author is already digesting the information for you, and they're repackaging it. And so it's like eating a TV dinner. Like, it's eating a meal where it's already on a tray for you. Here is the meat, here is the vegetables, here is the rice, and they just hand you the food. But a research paper is a little bit like you go and grow the food yourself, and you prepare the meal, and you're doing it from scratch. And so the analogy is that a research paper is meant to simulate what you'll face after you graduate, and that is the unfamiliar problems you have to be ready to teach yourself how to solve. Okay, so we're going to start off a little bit differently than we normally do today, but I'll just mention one other announcement before we get into that. The final exam is 2 weeks from tonight. Next week we'll have a brief review session where I'll talk specifically about the exam and what you should do to prepare for the test. Now, we're going to actually start our review tonight, though, with in-class exercise 14. And this is a little bit different than what we've done before. I have okay, I'll let you hold on to those, though. I don't need to collect them. All right. Last week I forgot to give you the terminology slide for Chapter 9. So Chapter 9 was last week. That was the attached growth. So here is the terminology that you should review for the attached growth chapter that we did last week. And then here is the terminology that goes along with Chapter 10, which is the subject of tonight's class. So these are the things that, if they don't come up directly in tonight's lecture, you should seek out in the textbook and try and understand what each of those mean. What we're talking about tonight is anaerobic treatment. And we've had some brief sections previously where we've had anaerobic conditions inside of a reactor for example, when we were removing nutrients, conditions need to be anaerobic. But this diagram is a nice comparison between aerobic removal of carbonaceous material and anaerobic removal. And it kind of illustrates the benefits that go along with anaerobic treatment. When you have the opportunity to do it, number one, it generates less sludge volume. And so what this diagram is trying to show you is that in aerobic treatment, number one, you have to provide the oxygen. And that's expensive because you're providing the oxygen usually with a diffuser, where they have big fans blowing air into the diffuser so it can bubble up through the aeration basin. Even in the case of a trickling filter, where you're saving a lot of money compared to activated sludge, you still have to pump the water to the top of the trickling filter, and so you're still spending some money in the form of electrical costs to provide the oxygen. The other issue is that you've got a big sludge volume compared to here. It's showing about 10% of the carbon goes into the sludge, compared to 90% of the carbon can be directed into the generation of methane. And the nice thing about generating methane is that you use a portion of it to heat up the sludge that's being treated, but then a greater fraction of it can be recaptured and used as a resource. So here is a nice video that explains a little bit about anaerobic treatment. Let's pull that up.
Technology offering many benefits to society. Far too often, though, this method of organic waste treatment is touted only for its ability to produce renewable energy. However, anaerobic digestion also helps improve air and water quality, reduce greenhouse gas emissions, and can even be a source of job creation for local economies. Furthermore, the next generation of anaerobic digesters is at the center of a system of technologies capable of producing even greater benefits.
Digesters have been around for a while, but we've got new technology that allows us to take this to a better place economically and environmentally.
Traditional methods of dealing with the organic waste stream include sewage treatment plants, aerobic lagoons, compost yards, and landfills. However, unlike anaerobic digesters, these solutions more often than not consume rather than produce energy. Digesters come in many different designs. Some treat municipal sewage or urban food waste. Others process animal food. In this video, we will use the example of a rural, dairy-based system. But whatever their design, all digesters follow the same underlying concepts.
Anaerobic digesters are basically carbon conversion tools. They simply take the organic carbon that's inside the manure and turns it into a gaseous inorganic carbon, which is called biogas. Biogas is methane and carbon dioxide. It's the methane that we really want. We can use it for fuel or as power or electricity.
Without anaerobic digestion, manure management has traditionally been limited to simply storing untreated manure in lagoons and later applying the untreated liquid onto fields. However, this practice leads to potential air and water quality issues, such as nutrient overload into soils, release of phosphates and nitrates to water supplies, and emissions of odorous volatiles, ammonia, and greenhouse gases, such as methane and nitrous oxide. Anaerobic digestion, as part of a system of integrated technologies, can address all of these issues.
It gives us the diversification to have more than one item to sell, and also helps us control the nutrients, the manure, and that sort of thing.
At the center of the system is the digester itself, basically a sealed tank where the organic material is broken down. On this dairy farm, cow manure and potentially off-farm organics from the community are collected in a holding pit, then pumped into the digester. The tank mimics the digestion process of an animal stomach. Inside, the liquid is heated, agitated, and mixed in an air-free environment. This converts the solid carbon in the manure to biogas, which is collected, cooled, and used to power an electrical generator. The electricity can be sold to the local utility and sent out to the grid. The system itself creates the energy needed to keep the process going. Temperature and flow are maintained using excess biogas and heat reclaimed from the generator set. After the biogas is captured, the treated manure is pumped to a separator where the liquid is removed. The remaining solids can be used by the dairies bedding for their animals or even sold for profit as a soil amendment or peat moss replacement. The treated liquid is stored in a lagoon for watering crops. Unlike untreated lagoon water, this liquid is significantly reduced in pathogens and virtually odor-free. For the current generation of anaerobic digesters, this is where the treatment process usually ends. However, even greater benefits and value can be gained by adding additional components to the system. One example is nutrient recovery.
Anaerobic digesters by themselves do not do a very good job of treating the nitrogen and phosphorus in the manures or organic waste. If you have too much fertilizer, too much nitrogen and phosphorus, it can be harmful for the soil and the plants. That's the case at some of our large animal farms. Therefore, we need nutrient recovery units to be associated with our digesters.
Nitrogen, in the form of ammonia, can be reclaimed using a revolutionary new technology developed by Washington State University and its industrial partners. The process is far less expensive than existing methods.
We can collect it and then make it into an ammonia sulfate fertilizer that farmers traditionally have used for years. An added benefit is that during this ammonia production process, we cause the phosphorus to settle out. So we get a 2-for-1. These concentrated biofertilizers can be used by the farmer and displace what they presently are doing in buying fossil fuel-based fertilizers. A combined digester and nutrient recovery system is a win-win because we make renewable energy, we solve a concern with nutrients, and we make revenue for the local community.
Another add-on technology relates to the scrubbing and compression of biogas. In this type of system, biogas is converted to renewable natural gas fuel instead of being used to generate electricity.
We're just in the middle of a tip from petroleum-based fuels to methane fuels, natural gas, for trucking fleets and for cars. We have the technology now to produce renewable natural gas from the biogas that comes off the digester. It's clean to pipeline standards. It's available for vehicle fuel for half the price of diesel.
While biogas scrubbing and nutrient recovery are already at commercial scale, pyrolysis and other related technologies are currently in development and hold great future promise.
In the future, we'll be able to take this the next step to clean, even drinkable water.
Construction of anaerobic digester systems helps state and local economies as well. In addition to tax revenue, it is estimated that in the state of Washington, for example, each digester project creates 15 to 20 full-time jobs during construction and 2 to 3 permanent positions for its operation. Despite their initial capital cost, with well-conceived business models, anaerobic digester systems offer significant economic savings and environmental benefit over the long term.
Everything kind of comes in, goes around, and goes back out as something usable.
There are synergies with this systems approach. We not only have the digester, but we've got these additional units that we can plug on, and that requires more capital, but also generates a lot more revenue, making a more profitable package and making this more replicable.
The advantages of anaerobic digestion are well documented. Waste management, renewable energy, biofertilizer production, greenhouse gas reduction, and more. With the incorporation of existing technologies and development of future ones, the benefits will only continue to grow.
So, although that was talking about mostly animal wastes, of course the same principles apply for treating municipal waste and waste that's generated from humans as well. So these anaerobic treatment processes can be used along with suspended growth or with attached growth. You know, it can be used to treat the sludge that's going to come out of a clarifier of either of those. And there are a lot of different configurations of what goes on inside of that pit. In the video we just watched, it basically looked like they had grass growing on either side of the tank and then a concrete top on the tank. And so what's going on inside of that anaerobic digester is what we're going to spend some time talking about this evening. As far as the chemistry, what's happening inside, first of all, the complex waste components have to go through a process of hydrolysis. And so it's breaking down fat and protein into less complex molecules, triglycerides, fatty acids. And then the next step after that is that those products are turned into short chain acids. And let me show you a diagram here. So the complex waste is broken down into acetic acid. And then in parallel, both acid fermentation and methane fermentation are happening simultaneously to form carbon dioxide and methane. And so regardless of whether or not you have anaerobic digestion, that carbon is ultimately going to end up, much of it, back into the atmosphere. But the benefit of doing anaerobic digestion first is that you're going to have an intermediate step where the methane can be used to generate heat and electricity. So if we go back here, the methane fermentation, which is really the step that generates the value, is where you're converting alcohols and acids into the methane. So if we look at the scale of how much energy can be captured, this diagram, which is taken from the text, points out that in a typical treatment of aerobic treatment of waste, if you're going to be looking at a kilogram of COD that's removed, it would require about 1.9 times 10 to the 6 kilojoules to remove that kilogram of COD. By contrast, you have a net energy benefit for anaerobic treatment. And this is showing that you have to use some of the methane that's produced to heat up the wastewater, but then even after accounting for the losses of energy to heat the water for anaerobic treatment, you still have a net energy benefit. And so you're generating energy instead of using energy. There's less volume of sludge that has to be treated. And the reactor volumes are actually smaller as well. And the reason for that is that the waste is a lot more concentrated than it would be if you're doing aerobic treatment. The suspended solids concentration in an aerobic reactor can be 20,000 milligrams per liter or even beyond that, compared to typical solids concentration in an aeration basin of maybe around 2,000 milligrams per liter. Another thing that's kind of nice is that the anaerobic digesters respond well to peak loads. And remember that whenever you have a living system, it's difficult to give it a lot of food and then stop, and then give it a lot of food and stop. And at the beginning of the semester, we talked about the importance of flow equalization basins to try and even out those peak variations in flow rate and substrate loading. But anaerobic digesters actually do respond well after long periods without feeding. So that if you only are receiving an industrial waste once a week, then the anaerobic digesters actually can handle that fairly well. They can spin back up into high kinetic activity after a period of low kinetic activity. So, you know, this picture is meant to represent that the tortoise versus the hare. Anaerobic treatment is the one that has the faster kinetics, but in the end, did I say aerobic treatment? Aerobic treatment is faster, but anaerobic treatment has so many benefits that it really has a lot of promise, although there are a few disadvantages and concerns that we have to be aware of. And one is that because a lot of carbon dioxide is generated inside of the aerobic digester, CO2, that forms carbonic acid. And so the pH will go down of the wastewater that's being treated. And so typically you have to add alkalinity to wastewater that's going through anaerobic treatment to try and stabilize, unless it's already a well-buffered solution. So the requirement of adding alkalinity is because in this process you can see that the complex waste, as it's being broken down, a lot of CO2 is being formed. And the CO2 is going to speciate into carbonic acid. Just like when you have Pepsi or Coke, the pH of something with a lot of CO2 dissolved in it is going to be much lower than neutral. And so that's where the requirement of alkalinity addition comes from. Another thing is that although it's really good at converting dissolved COD into methane, there's not a lot that the anaerobic digester is going to do for suspended solids. And so this typical suspended solids effluent quality is still going to be above treatment limits. And so it's not just a one-step solution and then it's ready, the effluent is ready for discharge. That's not the case, primarily because of suspended solids. And then the other thing is that there can be long startup times, 3 months or even more, before the reactor is actually performing at steady state. And as it mentioned in the video, it is good for breaking down carbonaceous pollutants, but the anaerobic digester itself doesn't remove nutrients. And so it was showing in the little diagram, the animated diagram they kept coming back to, that you have to have separate steps to try and remove the nutrients and then recycle them as fertilizer somewhere else. It's not in the anaerobic digestion that nitrogen and phosphorus can be removed. And also, in the previous slide, it was showing the necessity of diverting some of the methane to heat the anaerobic digestion reaction. If that is lost and the liquid starts cooling off, then there is a huge reduction in the efficiency of anaerobic treatment when the temperature goes below 20 degrees Celsius. Some of the anaerobic digesters can be very susceptible to toxic substances, and because hydrogen can be in wastewater, if hydrogen sulfide is formed, then that can cause odor problems or corrosive gas, and it's also a gas that's harmful for people, as we've talked about hydrogen sulfide before. So it's an anaerobic environment. That means that sulfide can go to H2S. So here's just a couple of terms that come into play when we're talking about anaerobic treatment: yield. And the efficiency of anaerobic treatment is it's going to reduce the amount of biomass that ordinarily would be going into sludge by about 6 to 8 times. And so that's why these are so efficient at generating really low sludge solids, is it breaks down into such into the most basic elements. Instead of breaking a complex carbon chain into a less complex carbon chain, ultimately it breaks all the carbon chains either down into methane or carbon dioxide, and so there's just less of the carbon left over going into the sludge solids. And so the organic loading rates are extremely high. If you talk about how many kilograms of COD there are per cubic meter of volume of the digester. So these loading rates are 10 times higher than we would see for the loading rates of an aerated secondary treatment basin. So you see, compared to aerobic treatment, the max would be 3.2 kilograms per cubic meter of volume, compared to 32 kilograms of COD per cubic meter. We've already talked about alkalinity and how the reaction basically consumes alkalinity because CO2 is speciating into carbonic acid. And the problem with temperature is when it gets below 20 degrees Celsius, part of the chemical reaction gets stuck. Fatty acids accumulate. So let's go back to this chemical diagram. The methane fermentation is particularly sensitive to temperature, and so acid fermentation isn't. And so part of it, it's a two-step process, but one of the two steps stops below 20 degrees Celsius, and so you just have an accumulation of intermediate products. And when that happens, when you have the accumulation of intermediate products, then foaming can occur inside of the anaerobic digester. So it's a real challenging issue when the temperatures go too low. And then the other thing about it, remember, it said in excuse me, it said in the video that you have to have additional treatment beyond the anaerobic digestion, especially for the removal of nitrogen and phosphorus. So where would you use anaerobic treatment? Here are some of the perfect places for anaerobic treatment. It's good when there's a high BOD. It's good when there's less nutrients. Since it doesn't remove nutrients, we'd love to find an application where that's not going to be an issue. But places where there's already an elevated water temperature is going to be good as well, because that's just going to mean that you use less of the methane to heat the water up before it's treated. So breweries, where the water that's coming out of an alcohol distillery or a brewery is heated in the process of using it, that's great. Food processing in general, typically the water is used not only to process the food, but then to also cool the food products, and so the water itself is warmer than it otherwise would be. So here's just a few cases of the industrial wastewaters that anaerobic digestion can be pretty effective for. Food processing wastewaters have really high COD concentrations. If you don't have at least 1,500 milligrams per liter, then that's not enough for the methane to generate enough energy. So you can't just have, like, instead of secondary treatment, an anaerobic digester. That's not a high enough COD. It has to be something more concentrated than that. So it could be the sludge solids coming out from underneath the secondary clarifier. That would have a high enough BOD concentration, but not just the raw water that's going into secondary treatment, because a typical COD concentration of the wastewater might only be around 200 milligrams per liter. Here in Huntington, when we went to the treatment plant there, they said that they have a really low strength wastewater, and theirs is about 100 milligrams per liter for the wastewater. But the sludge that's coming out of the clarifiers might be up in this range where it would be effective for anaerobic digestion. So how much alkalinity is going to be used depends on partly the temperature and the speciation of carbon dioxide into carbonic acid, and maybe if you haven't yet taken the aquatic chemistry class, you'll take that in the future. I think that's going to be offered in the fall, and I'm sure you'll go through calculations relating to acid dissociation. Another thing that factors into it is what fraction of liquid gets into the gas phase. And inside an anaerobic digester, it's sealed. That's what makes it anaerobic. But it's not liquid to the very top. We'll see some diagrams of these anaerobic digesters later tonight, but they have lids on them. Part of them is liquid. Part of it is gas. And that gas consists of CO2 and CH4, methane. So the CO2 that's in the gas above the liquid is going to be dissolving down into the liquid. And that's what Henry's law describes as what fraction of the gas will dissolve into water. The microorganisms that exist inside of an anaerobic digester do require trace quantities of nutrients to be present, and typically these nutrients are available in excess. And so usually it's not required for wastewaters to be seeded with these nutrients, but it might be the case, like one of the perfect applications that was shown in the previous slide is it was saying like soft drink bottling plants, where you've got, you're cleaning out the bottles, maybe if it's a plant for the reuse of bottles that are being recycled, you have to wash the bottles, and so the sugar water that's in the soda has to be broken down. It's a really high COD. Well, in the case of Pepsi, it may not have cobalt or iron or sulfur in the water that's being treated. And so in that case, it might be that the nutrients have to be seeded for the anaerobic treatment to be effective. The flip side of nutrients, which sort of stimulate growth and are required for it, is inhibitors. And these are things that slow down the anaerobic digestion. That's not the same thing as completely stopping it, though. And sometimes we confuse the idea of an inhibitor with something that will stop the anaerobic digestion process completely. And so what this first table is showing is what concentration is required to moderately inhibit or strongly inhibit the anaerobic digestion process. And so you can see, just as an example, sodium, which is added to roads during the winter time when salt is put down on the roads to try and melt ice, that can end up in wastewaters, but it requires a pretty high concentration of sodium before there's inhibition of the anaerobic treatment process. So it requires a lot of some of these things. But this next table, the concentrations of some organic pollutants don't necessarily have to be high at all. These are very low concentrations, millimole concentrations, that will result in a 50% reduction in activity of methanogenesis. So that's the secondary reaction that's happening of the fatty acids being converted into methane. And so lauric acid, you can see as an example, if you have 2.6 millimoles, meaning 2.6 times 2.6 millimole per liter, then the concentration would be 50% of what it otherwise would have been. Over time, though, you can have a shift in the microorganisms that are present inside a reactor, and the activity can recover. You know, if it's going to be a persistent inhibitor, the acclimation process means that it might be able to get used to some of these pollutants over time. And one way to kind of protect anaerobic treatment is to have it in sequence, or to have, in other words, like a plug flow reactor, where instead of just having the incoming liquid going and spread out through the whole reactor, if you have several different reactors operating in series, then that would give you a chance to protect the methanogenesis, which is more sensitive to toxics. So just to do some calculations tonight, let's take a look at the quantities involved with anaerobic treatment. Here we've got an example that's relating to the formation of methane gas. And just as a typical rule of thumb, what we know is that every gram of COD that gets converted inside of an anaerobic digester is going to generate about 1/3 of a liter of methane gas. And that's at standard temperature and pressure of 1 atmosphere and 20 degrees Celsius. Now we can use the ideal gas law to predict what would be the volume of gas that is generated under conditions other than standard temperature and pressure. So if we're pressurizing the gas for use as a fuel, or if the gas has been heated up during the storage process or during the process of methanogenesis itself, then it may be a different volume. So just to get a feel for that, let's consider the case of we've got wastewater coming from a slaughterhouse, and we want to find out how much methane would be generated. And these are realistic values here. If you have 1,200 cubic meters per day of a wastewater coming from a slaughterhouse, and The anaerobic treatment is used to remove the BOD from 5,000 down to 60. Then what we want to know is what volume of gas would be generated in a case like this. And so the way that we do the calculations, first of all, is that Q is 1,200 cubic meters per day. That's the liquid flow rate. The initial concentration is 5,000 milligrams per liter. The effluent concentration coming out of anaerobic digestion is 60 milligrams per liter. So the delta C, the change in concentration of carbonaceous material, is just the initial minus the effluent concentration. So that's 4940 milligrams per liter. So how much removal in terms of mass is there? If we want to know a mass flow rate, then that's going to be the change in the concentration times the volumetric flow rate. So that's the 4940 grams per cubic meter that's being removed, and the liquid flow rate of 1,200 cubic meters per day. So this is going to be 5.928 times 10 to the 6th grams per day. So that's how much BOD is getting removed. You can think of it that way. So the typical rule of thumb is that you have 0.35 liters per gram of COD. And so if we multiply this by 0.35 liters per gram, that means that we're yielding 2.075 times 10 to the 6th liters per day of CH4, and that's at standard temperature and pressure. But we don't have standard temperature and pressure. What we want to do is pressurize the gas to 20 atmosphere, and it'll be heated to 20 degrees Celsius. So the last step of our problem here is to use the ideal gas law to convert what we've got from the calculation so far into the conditions of the gas once it's pressurized and heated. So we'll set it up this way. We know that PV equals nRT. In other words, P1 V1 divided by T1 is equal to R times N, which is equal to P2 V2 divided by T2. You probably remember these ideal gas laws from chemistry. So what we're going to do is rearrange it. We're going to solve for the volume of gas at condition 2, which is pressurized and heated. And that will be T2 P1 V1 divided by T1 P2. I've just rearranged the gas laws to solve for V2. Okay, so what is the substitution here? T2 would be at 473 Kelvin. That's 200 plus 273, which is the conversion factor between Celsius and Kelvin. P1 is 1 atmosphere. V1 was 2.075 times 10 to the 6th liters. Okay, and all of that is divided by T1, which is 293 Kelvin, times P2, which is 20 atmospheres. Okay, so V2 should be, once we compress the gas and it's heated, 167,471 liters. That's how much gas we're going to get out of this system. This is actually a pretty easy calculation. You know, it's easy to predict how much methane gas you can get out of treatment if you use this rule of thumb of about 0.35 liters of methane for every gram of COD. That's a lot of energy that you can recover. Any questions about the example? All right, let's take a quick break. We're more than halfway through the time that we've got allocated for the lecture. So let's pick back up in 5 minutes. Okay, just to reiterate that in an anaerobic environment, hydrogen sulfide can possibly form. And malodorous means it smells bad. Toxic means that it's very dangerous to human health. And in fact, if you do a Google search of hydrogen sulfide, like a Google image search, most of the images you'll find are of people laying on the ground. Like, it's not that they're actually injured, it's drills that wastewater treatment plants go through, confined space training, and people who work on sewers have to go through a lot of training on how to follow the buddy system so that if somebody gets overcome by hydrogen sulfide gas, you can rescue them without putting yourself in risk. So toxic, we're not goofing around here. It's really a dangerous gas. Corrosive, you can see from the pipe here that it's really chewed through steel without any trouble. And the other thing about it is it can dissolve in water, and so it can not only be in the gaseous state, but it can also be transformed or transported long distances dissolved in the water that needs to be treated. And so if it is in a wastewater treatment plant, then the origin of hydrogen sulfide was as sulfate, sulfite, thiosulfate, and then bacteria turn it into hydrogen sulfide in the absence of oxygen. And so one of the issues why it's especially a problem inside of an anaerobic digester is that it can slow down methanogenesis. It can, rob you of the methane that you're trying to form because you want to turn that into electricity. And the text quotes that as low as 50 milligrams per liter of hydrogen sulfide can reduce the methanogenesis by 50%, and so it can really slow down. You do have to have some sulfide in order for there to be methane production, but you need sulfide, not necessarily hydrogen sulfide. So it's sort of like you need a little but not too much. The other thing is that the toxicity of hydrogen sulfide to the bacteria that are in the anaerobic digester varies based on the pH of the water and what type of organisms happen to have set up inside of the reactor. And so there's, it's not always as cut and dry as 50. That's why there's a range here of how much hydrogen sulfide is required to start cutting back on the methanogenesis. This figure shows at what pH you're going to have hydrogen sulfide present versus the sulfide ion. And so the higher the pH, if you've got a pH of 9 or 10, then the vast majority of it is going to be as the sulfide ion rather than as hydrogen sulfide. Ammonia is also a problem for the generation of methane. And that's because it can interfere with the conversion of the intermediate alcohols into methane. And likewise, pH is important for speciation. You can see that it is free ammonia, NH3, and NH3 is most present at lower pHs. And at higher pHs, I'm sorry, I said that the other way around. NH4, ammonium ion, is the majority of what's present until you get to a pH of above 9, and then the prevalence of NH3, which is free ammonia, takes over. So at a pH of 7.4 at neutral, then only 2 to 4% of the ammonium is as free ammonia. So you can have a fair amount of ammonia inside a solution the text says that between 5,000 and 8,000 milligrams per liter are tolerable, and you'll still have methanogenesis if the reactor has adjusted to that over time. But initially, before acclimatization, then as little as 100 milligrams per liter can start to be toxic and slow down the generation of methane. And so the nutrients not only aren't removed, but the nutrients in excess concentrations actually can interfere with the primary objective of anaerobic treatment, which is to break down BOD into methane. So for the next couple of slides, we're going to look at pictures of different reactor configurations and talk about the pros and cons of certain configurations, and look at the typical loading rates, how much COD is going to go into each cubic meter of volume. And just the simplest of them is a complete mix suspended growth anaerobic digester. And you can see that the influent comes into a tank that has an enclosed headspace above it so that no oxygen is in contact with the liquid, and also so that the gas that's generated can be captured. Inside of here, the residence time of the liquid and the solids is the same because there's no recycle of solids. And so the solid particles, meaning the bacteria and the suspended solids, the mixed liquor is going to have the same storage time as the water inside of this reactor. Between 15 to 30 days is what's required. And there's a video here that illustrates that typical anaerobic sludge digester. And this is in Michigan.
This anaerobic digester used to reduce odor emissions from new food waste and biosolids, create a closed cycle for recycling organic material, and generate renewable energy. The digester uses dairy, drying all food waste, biosolids, which are nutrient-rich organic materials, and other organic material from campus and the greater Lansing area.
All right, so what's going into there is food from campus, so what's left over from Harless Dining Hall, right? They have some animal manure, and then biosolids from wastewater treatment, so sludge. So what's going in here is sludge, food, and animal manure.
Once delivered, the food and biosolids will be heated at 160 degrees Fahrenheit for 1 hour to eliminate any potential pathogens. The material will then be mixed with manure from the MSU Dairy Teaching and Research Center and pumped into the digester. The anaerobic digester is a sealed, airtight tank which can hold 300,000 gallons. Organic material will be heated to 100 degrees Fahrenheit and will remain in the digester for 20 to 30 days. Inside the tank, mixers in the digester evenly distribute microorganisms. These microorganisms break down the mixture, producing biogas and nutrient-rich digestate. Biogas, which is roughly 60% methane, is a form of renewable energy which will be used to generate electricity. The system will generate enough electricity to offset the MSU Dairy Teaching and Research Center by around 300 kilowatts per hour, with enough left over to help power MSU. The capturing and use of biogas will generate energy, shrink the carbon footprint of campus, and improve sustainability. What's left in the process is digestate, the nutrient-rich mixture that will be held in the final storage tank until it can be utilized. Mixers in the storage tank will minimize settling for the potential 2.7 million gallons of digestate. Any unused biogas can also be stored in a sealed headspace. The nutrient-rich digestate will be used to fertilize croplands or other biological treatment processes to fuel research opportunities. By utilizing anaerobic digestion technology, the organic materials from MSU will become resources. Renewable energy is created while odors are reduced and emissions are eliminated. This project is one example of how Michigan State University is actively working to improve sustainability.
Okay, so here we've got a similar configuration to what we just were looking at, but now there's a sludge recycle. And so taking a clarifier and separating out the solids from the liquids and recycling the solids allows you to have more control over the sludge age. The sludge age, that's a term that we haven't used a lot this semester. We've used SRT, solids retention time. Sometimes that's referred to in text as the mean cell residence time. Another word for that is sludge age. And it's talking about the average age of sludge solids. And the benefit of having a recycle is that, number one, you have the ability to have a more mature colony of microorganisms inside of the digester. It can increase the efficiency if you have an elevated concentration of solids particles inside of the digester. And remember that the digester is only effective with pretty high BOD concentrations. And so having a recycle step like this may get you a little bit more flexibility in terms of what types of wastes are suitable for treatment in an anaerobic digester. You can see that the hydraulic detention time is a lot less now. Half a day to 5 days is the hydraulic detention time. In the previous slide, your detention time needed to be 15 to 30, and that was the amount of time that both the liquid and the solids spent in the reactor. But by recycling just the sludge solids, now the water component doesn't need to spend as long inside of the digester. So in theory, the digester can be smaller than it otherwise would have been, because the volume of the digester is just a function of the volume times the time the liquid has to spend inside of the reactor. So by recycling, we're reducing the hydraulic detention time. Okay, the next one to look at is a sequencing batch reactor. And that was one of the questions that was on the concept check that we had earlier tonight. What is a sequencing batch reactor? We talked about sequencing batch reactors for suspended growth activated sludge. Well, it turns out that the same idea of a reactor acting in different sequences can also be used in an anaerobic environment. So let's take a look at this video. The video is actually about an aerobic sequencing batch reactor, but my guess is that we'd benefit from just thinking about what is a sequencing batch reactor and then apply that into anaerobic conditions. So here's just a pretty good video that shows a sequencing batch reactor.
With nearly 3 decades of batch reactor experience, Aqua Aerobic Systems continues to lead the wastewater industry with reliable and cost-effective treatment solutions capable of removing nutrients, reducing phosphorus, and producing reuse quality effluent. The Aqua SBR sequencing batch reactor system features time-managed operation and control of aerobic, anoxic, and anaerobic processes with flexible process control that easily adapts to changing effluent demands. Operation of the Aqua SBR is a 5-phase process, beginning with mixed fill. In this phase, flow enters the reactor.
Okay, so it's called a sequencing batch reactor. It's talking about the first of the sequences. The first sequence is the filling stage.
And a complete mix environment is achieved with a dedicated Aqua DDM mixer. The absence of dissolved oxygen and rapidly depleting nitrate levels create the ideal anaerobic environment, promoting biological phosphorus release. This phase also operates as a fully adjustable selector process to control filamentous organisms. In the react fill phase, wastewater continues to fill the reactor and aeration is introduced. During aeration, organic material is oxidized and phosphorus is absorbed, while ammonia is converted to nitrates.
Okay, and obviously, if we're talking about a sequencing batch reactor for anaerobic treatment, there wouldn't be any aeration. So we have to keep in mind that you can use the sequencing in both an aerobic environment or an anaerobic. And so today we're talking mostly about anaerobic digestion. This reactor would have a roof on the top so that there's no contact with oxygen, and they wouldn't bother aerating if what they're going for is anaerobic digestion.
Unique to the Aqua SBR is the ability to offer discrete intervals of aeration and anoxic treatment. These intervals can be controlled by simple timers and dissolved oxygen control. For more advanced oxygen control, the IntelliPro process management system can be utilized to monitor ammonia, nitrate, oxygen reduction potential, or phosphorus concentration. This advanced oxygen control module proactively adjusts oxygen levels based on changing conditions and delivers the exact amount of oxygen needed to the reactor at any given time. This is just one example of the IntelliPro system's process control capabilities. The Aqua SBR features a true batch reaction period, which is identified as the react phase. In this phase, the influent valve is closed as wastewater is diverted to a companion reactor or equalization basin.
Okay, so they're talking about during the react phase, it's no longer accepting incoming flow. So if that's the case, the incoming flow has to be going somewhere else. If it's not going into this tank, it has to be going someplace else. And so in a sequencing batch reactor, you always have to have more than one tank. And at the very least, you need to have two, because as soon as you stop the inflow to one tank, you have to be sending it to another. But ordinarily, there would be a lot more than just two reactor tanks at a sequencing batch reactor, because eventually they're going to start emptying this tank. And so there would be one that's emptying, one that's filling, and one that's reacting at the very least, and possibly more than that for the matter of redundancy. But what it's going through now is a reaction phase. And so in an anaerobic digester, they wouldn't be aerating, but they would have stirring. And so there would be mechanical stirring inside the reactor to ensure that the solids stay suspended.
Mixing and aeration continue to further reduce pollutants in the absence of raw wastewater. The react phase offers a positive treatment barrier to ensure ultimate polishing of the wastewater prior to settling and discharge. In the settle phase, influent flow is terminated and mixing and aeration equipment are turned off. Ideal solids-liquid separation is achieved due to the quiescent environment, allowing the reactor to function as a perfect clarifier.
When he says quiescent, do any of you know what the word quiescent means? Think about a normal clarifier. Like in Huntington, that clarifier always has water coming in and water going out. It's a tank, and it's supposed to be very calm inside the tank, because you don't want the water swirling around. If the particles are supposed to be settling, any sort of flow in or flow out of a settling basin is going to disturb the downward motion of the particles. And so one of the things that's really nice about a sequencing batch reactor is that it's completely isolated during the settling phase. And so the sludge solids can settle to the bottom without any sort of disruption of outgoing or incoming flow. And so this phase is also true of an anaerobic digester, is that you can get really good settling results and a nice thick concentrated sludge of the sludge solids that are left, because it's so quiescent. Quiescent means calm, a very calm environment with no turbulence inside of the clarifier.
As with all Aqua SBR treatment phases, operational flexibility allows the user to adjust the settling time to match the prevailing needs of the plant. Due to the batch feature of this process, the settle phase is unaffected by variations in flows that cause disruption to settling in conventional flow-through secondary clarifiers. The final phase of the Aqua SBR is the decant phase. At this stage of the process, the clarified water must be removed from the reactor, equally to the same volume that entered during the filling phases. Throughout the decant phase, influent flow is not allowed to enter the reactor, and the aeration and mixing equipment remains off. The robust design of the Aqua Aerobic decanter provides unequaled reliability in subsurface effluent withdrawal, with more than 3,000 units installed. Effluent quality is protected by two separate barriers, a stainless steel weir and a valve on the discharge pipe. This dual barrier prevents solids entry into the unit and further protects the system from solids discharge. To open the decanter, an electric actuator lowers the weir and the valve opens, allowing clear effluent to exit the system. Among its many features, the decanter floats and adjusts to varying water levels, assuring that only the highest quality effluent is being removed. The decanter closes when level indicators determine a low water level set point has been reached. The discharge valve closes and the weir seals against the flow, preventing any solids from entering the decanter during non-decant phases. In the final minutes of the decant phase, a small amount of excess biological solids will be removed or wasted to a sludge holding facility. This process is typically accomplished with a small submersible pump, which operates for only a few minutes per cycle, as needed to remove the thickened sludge.
So what they were talking about there is that rather than recirculating sludge, you suck some of it out and waste it, and then the rest of it you just leave in the tank, because pretty soon you're going to be pumping new wastewater in, and retaining some of the old mature sludge solids will accelerate or activate the process once it begins in the next cycle of the sequence. So I just wanted to show you that video because, you know, it wasn't specifically about anaerobic treatment, but I thought it does a really nice job helping you to visualize what a sequencing batch reactor does. And so that sequencing batch reactor concept can be just applied directly to anaerobic treatment. And this diagram taken from the text shows that there's these different steps. There's the feed step, react, settle, decant. The only difference between what we just saw and this is that it's showing conceptually there's a lid on the top of the headspace so that the gases are collected and to make sure no oxygen gets down and interrupts the anaerobic treatment. So any questions about an anaerobic sequencing batch reactor?
How is the bacteria staying alive? Possibly 200 days, is that all?
Well, the bacteria that are in there don't require oxygen. They're using other things as the electron acceptor. And so they are, they're specially adapted to anaerobic. In the same way that, remember, in denitrification, there are bacteria that are consuming nitrate and turning that to nitrogen gas. That's what they're using instead of oxygen as nitrate. So here, there are bacteria that are they're living on alcohols and turning that into methane. So for the reactors that we've looked at so far, here are just some typical values having to do with the yield, the decay coefficient. The decay coefficient just relates to how quickly the bacteria are dying. That's the kinetics of endogenous decay. Maximum specific growth rate. You know, these parameters should be familiar from the calculations that we did with activated sludge. And if you compare these kinetic values to the ones for activated sludge, you'll see that everything's slower with anaerobic treatment. It's a slower reaction, but you know, it's the trade-off of getting some energy out of it. So I like to show this diagram just because it sort of helps you to understand the complexity involved in trying to capture that gas. This is a special kind of anaerobic treatment called an upflow anaerobic sludge blanket. And in this case, this is not a batch reactor anymore. We're away from the batch reactor. Here, there's always water coming in and there's always water going out. And so in this reactor, the difficulty is that the water is flowing up through a sludge blanket. And so the water that's being treated sort of percolates through the sludge, which is settling downward. And so in one tank, you've got a little bit of a clarifier going on because the effluent liquid is going up and the solids particles stay in. But at the same time, you're also trying to capture the gas. Now the gas is going to bubble upwards, but you don't want the gas to leave out of the same weir that the effluent is captured from. And so this cross-sectional view just shows that what they try to do is put in baffles so that the gas is forced to go towards places where it can be collected, but the water can go around these barriers. The water isn't forced to go straight up like the gas is. And so water exits the reactor and is collected and sent on for additional treatment. So there's a video helps you to visualize an upflow anaerobic sludge blanket. So this is kind of like a specialized application. This is not just your standard activated sludge. I'm sorry, this is not just your standard anaerobic digester because of the configuration of continuous flow. It's not batch flow. It's the water is always going upward through that sludge blanket.
Methane is a global leader for anaerobic industrial wastewater treatment. Its granular-based technologies have successfully been applied in over 530 plants worldwide. Faced with our clients' demands for reducing investment and operating costs, we have developed the novel, cost-effective BioBed advanced system. UASBs are renowned for their high COD removal efficiency and the ease of maintaining granular sludge. EGSBs are more cost-effective and have a small footprint due to the applied high loading rates and the tall reactor design. The challenge in developing the BioBed Advanced Reactor was combining the excellent performance of the UASB with the cost-effectiveness of the EGSB. In granular sludge systems, it's all about keeping the biomass in the reactor. The advanced settler achieves multi-level gas separation, but also provides a large settling area for good biomass retention. Higher liquid and gas velocities are applicable, which result in a more compact design. In numerous full-scale systems, pilot plant testing and model hydraulic testing, the superior performance of the BioBed Advanced system has been proven. The system can be built as a completely closed system, ensuring no odor emission. The round steel tanks or square concrete tanks can be built up to 20 meters high. The compact settler is constructed in durable stainless steel and polypropylene. The settler price is reduced by using advanced manufacturing techniques. It can be transported cost-effectively in standard sea containers. The BioBed Advanced technology has been applied in numerous full-scale plants, treating pulp and paper, chemical and food processing wastewaters. The experience from full-scale plants has shown that the BioBed Advanced system is more stable and reliable, and thus achieves lower overall operating costs. The system can be completed with...
All right, we'll leave it there for that one. The point that it's making is that there's upflow for the water that's being treated, and what they were talking about there, the abbreviation UASB, upflow anaerobic sludge blanket, and then they were also in that video referring to these granular sludge nodules. And a granular sludge is kind of an interesting thing. It starts off as just an ordinary sludge, but over time matures into these nuggets that are floating around. And what makes them kind of desirable, the benefit of a sludge granule, is that it settles very, very quickly. When you have a solid particle like this, it's really easy to keep in place. And so they were saying that the towers can be shorter than usual because of high liquid flow rates. And you can achieve a high liquid flow rate if it's easy to settle the sludge. And so these granules are screened, and so that the effluent is much easier to keep separate from the sludge solids. And so that's the benefit of the granular sludge. Now, when they're designing something like this, they'll try and figure up on how thick the sludge layer is going to be. Here is the layer of the sludge blanket. It's important at the bottom of the reactor to try and diffuse the flow so that you don't have it all just coming in one jet, but diffusing it out ensures that the entire cross-sectional area of the tank is having liquid flowing up through it. And then the other thing that's important is, like I was mentioning before, some sort of a baffle system to collect the gas and separate the gas that's bubbling upward from the liquid that's going upward. Okay, so on the concept check, I asked about a plug flow reactor. And what we're looking at here is a baffled reactor that essentially is acting as a plug flow reactor where you have water flowing through a chamber and then another chamber and another. And I've highlighted that the plug flow configuration of a baffled anaerobic digester improves kinetics. And so who feels like they understand why a plug flow reactor is more efficient than a completely mixed reactor?
Plug flow reactors where you're introducing the liquid at different locations throughout the tank?
Well, it can. You definitely can have a staged plug flow reactor. Here it's not. This one that it's showing is not a staged plug flow reactor, but like if you have a pipe like this, water's flowing through the pipe. So this is the reactor. You could have the incoming waste, instead of just only having it come in the reactor at one place, you could have some coming in here, some there, some here. So this is what a staged plug flow reactor would look like. But this is just a plug flow reactor, so we're just comparing, like if you have a reaction and it's going to go into a tank and then come out of the tank, why is it that a plug flow reactor is going to have better kinetics than the same volume, but it's all stirred together? So this is the top one is a PFR, plug flow reactor, and the bottom one is a completely mixed flow reactor. So the reason why a plug flow reactor is better for kinetics, let's say you have 1 liter of the water that has to be treated, and it enters the reactor. At the beginning, that 1 liter has a very high concentration of substrate. Here is the 1 liter. It's all staying together in the plug flow reactor. It's not mixing everywhere. So that 1 liter is together, and the concentration of substrate is high. When the concentration of substrate is high, first order kinetics says the rate of removal will be high. But if you still take that same 1 liter of substrate and you put in a completely mixed flow reactor, instantly it's spread everywhere. And so instead of being all in one spot, it is all through the reactor, and the concentration of the substrate is low. And when you have a low concentration of substrate, the bacteria are acting more slowly. And so if you only are going to build a reactor that is 1,000 liters in volume, having 1,000 liters configured as a plug flow reactor is more efficient than 1,000 liters configured as completely mixed flow, because in a plug flow reactor at the beginning, the removal rate is very high. It's not until the end, down here at the end, the concentration is low and the rate of the reaction is low. So it's not removing very much BOD at the end, but it removed a lot at the beginning, and that's why the plug flow reactor has improved kinetics. And staging it is a way to even do better than an ordinary simple plug flow reactor. If you inject the substrate at multiple locations inside the plug flow reactor, then essentially you have different zones where the concentration is going to be high. So this anaerobic baffled reactor is a way of staging and separating the reaction. So the first chamber will have higher kinetics because it has higher substrate concentration than towards the end. And the added benefit of that is stability against shock loads. Because if you suddenly have a lot of BOD coming in or a toxic substance, it will only affect a smaller component of the reactor. It won't affect the whole reactor all at once. It'll sort of keep that isolated rather than spreading it out every place. Any questions about the anaerobic baffled reactor? Okay, here's a diagram that's just showing the performance of an anaerobic baffled reactor. And probably the thing that we've been looking at the most tonight is the COD loading. This is the mass of COD per every volume of the reactor. And what we've been seeing is COD loadings up as high as 35 kilograms of COD per cubic meter for some of the reactor configurations. Okay, so let's just revisit these announcements one last time before we finish for tonight. Remember that the big thing for next week is those research papers. I have office hours on Tuesday and Thursday, but for you guys, I'm available anytime. Graduate students have, they're a little more important than undergraduate students, right? So email me anytime and I'll respond as quickly as I can. Come to my office, and if I'm in, I'll make time for you, especially because I know you may have questions leading up to finals and leading up to the research paper. So I welcome you anytime. Hope you have a great week, and I will see you next Wednesday night.